Good morning, students. So today we will talk about the Knuth-Morris-Prat algorithm. So it is one of the best known linear time exact pattern match algorithm. And it actually does a pre-processing to achieve this linear time complexity. So first we will talk about what is this pre-processing that it does, and then we will see how is this pre-processing step used in order to achieve the linear time complexity. So the idea behind the Knuth-Morris-Prat algorithm is to define something called a prefix function. Okay. So prefix function, which we will denote by pi. Okay. So it pre-processes, the idea is to pre-process the pattern itself. Okay. You pre-process the pattern itself to find matches of prefixes of the pattern with the pattern itself. So you construct a prefix of the pattern and you match the prefix with the pattern itself. Okay. So and you keep on doing this, and in the in this way you construct something called the prefix function. So it is typically defined as the size of the largest prefix of the pattern, say starting from 0 to j minus 1. Okay, the size of the largest prefix of this, that is also the suffix of p1 to j. So something which is the largest prefix of p0 to j minus 1 and is also the suffix of p1 to j, that is a sliding window of 1. So this is the prefix function. This defines the prefix function. Okay. So this also defines how much. So in other words, as we will see through an example soon, how much the last comparison can be reused in case the match fails at a point. So basically, you keep in your memory the amount of prefix that has been matched so far. Okay, and if there is a failure at a point, you backtrack to that position till which you are uh, sure that the prefix was matching, and then you again start recomputing. So basically, this allows you to avoid backtracking on the main string. So since you are backtracking on the pattern, which is typically much smaller than the main string, it allows you to, so this is the beauty of the algorithm. So as you will see that you will only backtrack on the pattern, okay, rather than backtracking on the main string, which might cost you larger. Okay. So the algorithm in a nutshell to compute the prefix function is as follows. So we'll first write the algorithm and then we will try to see how we build up the prefix function table, and that will make things more clear. So let's say M is the length of the pattern P, and let pi, which is the prefix function, pi1 be set to 0. And we also have another variable, the potential variable, which is set to 0. Now we start from Q, which is an index, to M. So you see we are traversing on the pattern itself. Okay. And we check while k is greater than 0 and pk plus 1 is not equal to pq, do k pi k. Okay. End while. If pk plus 1 is equal to pq, then k equals k plus 1 and end if. And then finally pi q is the current value of k and end for. And then finally you return pi. So you see what is happening here is like you are advancing q one by one and you are checking whether uh, the current value of um, pk plus 1 is equal to pq, and so one is starting from um, 0 and the other is starting from 1, or you can imagine one is starting from 1 and the other is starting from 2, whatever way you index your string array. Okay. And you keep on doing this as long as there is no mismatch. Okay. The moment there is a mismatch, you get into this particular segment. Okay. And in this particular segment, what you do is you backtrack up to the point where pk plus 1 has been equal to pq. Okay. And you set the value of k back to that prefix function. Okay. So that you are at the correct location from where you can again start matching the prefix. And this continues. Fine. So we will look into an example which will make the thing much more clear. Let's say we have the following pattern. So M initially is 7. Okay. Pi 1 is 0 and k is 0. Now with these values you start traversing. So we will write step by step what is happening. Step 1. So now at this point your q is 2, right? You start with your q as 2 and your k is initially 0. Okay. Now you find out p k plus 1. Pk plus 1 is P1, which is A, right? And PQ is equal to P2, that is equal to B, right? However, at this point, you will not enter the while loop because your K is not greater than 1. Okay. So you will bypass the while loop, and then what you observe is that pi 2, so finally k remains 0 and your pi 2 becomes 0. Pi 2 is set to the value of k, which is 0, right? So now after this step, you have pi 2 as 0. Okay. So here your q is 2, k is 0, pi 2 is 0. Fine. Next step. Step 2. What happens here? P k plus 1 is equal to P1 is equal to A. P q is equal to P3 is equal to A. Therefore, now your Pk plus 1 is equal to Pq in this case. Okay. Therefore, you do not enter the while loop and your k equals 1 and pi 3 is equal to k is equal to 1. Okay. So now after this step, your q is 3, k is 0 and pi 3 is equal to 1. So you can proceed like this, and the interesting thing starts happening at the point of step 5. So then you will have step 3, okay, where you can do it yourself. I'll just write down the status. of the table. In this step, your pi 4 becomes 2. Then step 4, q is 5. Here your q is 4, k is 1. Q is 5, k has become 2, and now this becomes 3. At this point, pi 5 is equal to 3. At step 5, you will see your q is equal to 6, k is 3, and now let us try to compute the state of the table. So now pk plus 1 here is P4, right? And PQ is P6. We check whether P4 is equal to P6, which is not true. Okay, so therefore we set K to pi 3, okay, as per the algorithm. That means now K becomes 1. Okay, so since K is still greater than 0, we will again run through the loop and check whether Pk plus 1 is equal to Pq once again. Here now Pk plus 1 is P2 is equal to P6 or not, which is again false, and therefore we will again reset the value of K to pi k, which is K is set to pi 1, which is 0. Okay, so now K has become 0. Okay, now you come out of the while loop because your K has become 0, and now you check whether P0 plus 1 is equal to P6, which is also not true. Therefore, your pi 6 is set to the value of K, which is 0. Therefore, you have at position 6 the value of pi set to 0. Next, and the final step is step 6. Where your Q is 7, K has been reset to 0, and the state of the table is this. Okay, so now since your K is 0, so you will not enter the while loop. Right? So you will directly check whether Pk plus 1 is equal to Pq. Here Pk plus 1 is P1 and Pq is P7. Okay, and this is true, both are A. Okay, so therefore your K becomes K plus 1, which is 1, and your pi K is set to, sorry, pi 7 is set to 1. Okay, so therefore here your new K becomes 1 and pi 7 is set to 1. Let's say n is the length of the string S. Okay, and m is the length of the pattern P, and pi, as earlier, is the pre-computed prefix function. We usually store it in a prefix table. So you will see that, and again here is a potential index which is Q. You will see that the code that we will write here is very similar to the code for finding the prefix function. Okay, so basically you will iterate on the string, and every time you will do the necessary backtracking only and only on the pattern and not on the string. Okay, while, sorry, first iterating on the string for I 1 to n, while q greater than 0 and p q plus 1 is not equal to s I, q is set to pi q, end while. Now if P Q plus 1 is equal to Si, then Q is set to Q plus 1, and if Q has become equal to M, then you set Q to pi Q, and and for. That's all. So here again, this is your step which will enable you to backtrack like the way we did the prefix function computation. Okay, and then this is the portion which will actually allow you to proceed, okay, on the string step by step and accordingly modify the value of Q. So if your Q has become at some point in time equal to M, then you set Q to pi Q and exit. Okay, so we will see an example to illustrate the situation in a more detailed way. Our string is as follows. Let's say this is our string and this is our pattern. Okay, so now we will start executing the algorithm that we have written just now. So initially n is 7, sorry, m is 7, n is 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. Okay. So now step 1. I is 1 and Q is 0. So we compare P1 with S1. Okay. So now what we see is that P1 is not equal to S1. So what we do that P is shifted 1 position. right? Okay. Now, step 2, I equals to Q equals 0. We again compare P1 with S2. So P1 and S2 matches, right? So at this point, the state of the two strings are as follows. So this is where the pointers for the two strings and pattern are standing at this point. Okay. Now we move forward. So after this point, since there is a match in step 3, I is equal to 3, Q has become 1. Now we compare P2 with S3. Okay. So now at this point, P2 does not match with S3. So we will backtrack on P. We backtrack on P, compare P1 with S3. Okay. At this point, the position of the two pointers are as follows. So this is a mismatch here. And now we therefore backtrack and compare with S3. Step 4. I has moved to 4. Q has again become 0. Now compare P1 with S4. Okay. P1 does not match with S4, right? So then in step 5, I equals 5 and Q is still at 0. So now we compare P1 with S5. Okay. And there is a match, right? So now the condition of the two strings are as follows. So at step 4, sorry, this is step 5. At step 5, there is a, we again find a match. Let's see what happens in step 6. Step 6, we have I equals 6 and Q has again got incremented due to the match in the previous step. Now we check P2 is equal to S6, which is true. Okay. So that is a, so we have found that P2 is equal to S6. And again in step 7, if we continue, I becomes 7 and Q becomes 2. P3 is matched with S7. And again, this is true. Okay. Step 8, I has become 8, Q has become 3. Now you compare P4 with S8. Again, this is a match. Okay. Step 9, I equals 9, Q equals 4. Now you compare P5 with S9 and again this is a match. Okay. At this point, the status of the two strings are as follows. So you see, we have got 4 places of match at this point. However, the unfortunate situation is at step 10, your I equals 10, Q equals 5, P6 is compared with S10, and this is not a match. Okay, so that means you backtrack on P, comparing P4 with S10. Why P4? Because Q has been now set to pi 5, which is from the table you get to be 3, and therefore you are checking PQ plus 1, which is 3 plus 1, P4 with S10. So you see, you don't have to go back to the beginning of the string. You just, backtrack on the pattern, and accordingly you remove those many places from the string which you do not need. So you see, now you have gone 2 places back. From P6 you have gone 2 places back. So you will have to discard 2 places in the string and again start matching the pattern from the next point onwards. Okay. So till now your match started, you see, 1, 2, 3, 4, from the 5th place your match started. But now, since there has been a mismatch and you have to go 2 places back on the, you have to backtrack 2 places on the pattern, that means 2 of your initial string matches are also gone. So your current state is you have matched AB with this AB. Okay, you don't need to recompute these matches anymore, but this part of the match is gone. Now after this step 10, we have step 11, where I is 11 and Q is 4. You compare P5 with whether P5 is equal to S11 or not, which is true. Okay, then you go to step 12. I is equal to 12. Q is equal to 5. You match P6 with S12, is again true. And then you finally have step 13, where I is equal to 13 and Q is equal to 6, and you compare P7 with S13, which is a match. So at this point, the status of the 2 strings are such that the pattern is completely found in the string. small mistake here in the entries. This is D A C B A B B B A C. So the matter of the fact is, at this point, you have a complete subsumption of the pattern in the string. And you see that you, in 13 steps, which is order of n, you have been able to find a match of the pattern with the string. And the number of shifts required in this case is I minus m, which is 13 minus 7, that is 6. Okay, so I would not even have advanced if we would have got the match earlier. Okay, so so then in that case the shifts required would be much less. Here, since we had to advance I to almost the last step, okay, so we have to have shifts of 6. So actually n is 15, but we had to go only till 13 to find a complete match of the pattern with the string. Okay, and then once this is done, one can again restart the process to find out the next part of the string where the pattern can be found. Okay, so in this way, the Knuth-Morris-Prat algorithm executes in order n plus m time and is known to be one of the best algorithms. The only problem is when your pattern becomes very big, then maintaining the prefix function is a bit costly. Otherwise, it is one of the best models for string matching. So we stop here, and this also ends our syllabus for algorithm 1. And I hope you have at least got some basic concepts about how in real life algorithms are designed, and I hope you will carry forward these ideas into not only the algorithm 2 course, but also in different other courses where you will very frequently need the advanced data structures that we have taught you, as well as various algorithms, including this pattern matching sort of algorithms, hash tables, graphs, etc. Thank you very much.